All right, welcome. We're here in chapter 12, last chapter before we start our review for the AP exam. So we'll start hitting with three sections and we'll split them up in halves for the most part. So again, we're going to talk about the chi-squared test and for goodness of fit. So we're going to introduce that, break that into two sections here. Again, I've got our learning targets here. As we're going. So here's an interesting problem. We have Consumer Affairs Department of Mars Incorporated says that the distribution of color for its M&M's milk chocolate candies produced at its Hackettstown, New Jersey factory is as follows. Okay, so it looks like we have a little bit more orange and blue and the rest are kind of there. So let's get those percentages. So Jerome's class was wondering if the distribution of color in a large bag is differed from the claimed distribution. And here's what they got. They took 60 candies, a random sample of 60 out of the bag, and here's what they got. All right, so the distribution of color in the large bag of M&M's milk chocolate candies is the same as the claimed. That's going to be our null hypothesis, and our alternative is going to be that it's not the same as we go there. All right, now again, we can use it in symbols. We could say that, put the actual proportions down if we wanted to, and then the null hypothesis would be that, at least two of those proportions are incorrect, again, as we go. So, again, don't state that the alternative hypothesis in a way that suggests that all the proportions in the distribution are wrong, just, that just some of them are, or so anyway, how many candies of each color should Jerome's class expect to find in their 60 candies? Well, assuming if we go by those proportions, we multiply 60 times each of those, we can see the following results. Now, the expected count for category I in the distribution of a categorical variable is n times the proportion of category I specified by that null hypothesis. Okay, so again, here's what we got. We've got some observed values and what our expected are. Okay, so now we kind of take a look at, okay, how do we organize all that information, and how likely is it that the differences in this larger or would occur just by chance in that distribution? So let's figure out how to do that. Now, the statistic we're going to use to make that is called the chi-squared test statistic. All right, so how do we figure that out? Well, what we're going to do is we're going to take the observed count minus the expected for each one of those, square it, divided by that expected count, then we're going to sum them all up. Okay, so as we look at our M&M's category, again, we take those, and again, the idea of squaring things is keep it all positive. And again, we're kind of adding those up. So our chi-squared number that we get in this case is going to be 9.8. And again, in the tech video, we can certainly show you, and we'll show you in class exactly how to use that to find that value. So we can get that just to spit it out for us if we want to. So that's kind of nice. All right. So anyway, so let's look at another problem. Carrie made a 6-sided die in her ceramic class and rolled it 90 times to test if each side was equally likely to show up. The table summarizes the outcome of her 90 rolls. Now, again, the hypothesis would be that the sides of Carrie's die are equally likely to show up, and the alternative would be that they're not equally likely to show up. Okay, so let's talk about this. Again, we should see that each of them should be 15, right? If it's all the same, take a sixth of 90, you should have 15 for each side, which is of course different than what she got, which we'll have to see what does that mean. So we take each number, subtract that 15, square it, divide it by 15, and then add all those up. We get a chi-squared value of 14.41. Okay, so that's the process that we're using there. And again, we can use our calculator to help us out too, and we'll show you that. All right, so now we use software. Now let's say we did the M&M's candy problem again, taking 1,000 random samples of size 60 from the population given by the Mars Inc. Now here are the values of that chi-squared test statistic for those 1,000 samples. All right, so that's what happened. So the larger values of chi-squared give more convincing evidence against the null hypothesis and in favor of the alternative. So our estimated p-value is 87 out of 1,000, which is 0.087, and because we had in 87 of the 1,000 simulated samples, the value of the chi-squared test was at least 9.8. is the observed test statistic. That's what we got when we did Jerome's class. We had a 9.8. So in that case, we're saying, yeah, it's p-value there is 0.087. So 8.7% chance of that happening. So the chi-squared distribution is defined by a density curve that takes only non-negative values and is skewed to the right. A particular chi-squared distribution is specified by its degrees of freedom. Okay, so again, degrees of freedom is going to be one less than your counts that we have here. So you can kind of see what happens as we kind of get higher degrees of freedom. The density curve, it becomes less skewed. And then the mean of a particular chi-squared distribution is equal to its degrees of freedom. So that's what that is. And then for the degrees of freedom that are bigger than 2, the mode is the degrees of freedom minus 2. So take that as you look at those values that we have there as we answer those questions moving forward. All right, so there are 6 color categories for the milk candy. So degrees of freedom would be 6 minus 1, so it would be 5. Now, the p-value is the probability of getting a chi-squared value of as large or larger than the 9.8 that we figured out before when the null hypothesis is actually true. Okay, so as we take a look there, so that's graphically what we're looking for. Degrees of freedom is 5. We have a chi-squared value of 9.8. So we're looking for that area under that curve to the right. So we get that value or bigger. And we look at that p-value. Now, looking at a chart, if we look at the back of our packet that we had, we'd have to say, yeah, that 9.8 kind of falls between 0.05 and 0.10. So again, the chart isn't always exactly the most accurate thing in the world. We can definitely put that into our calculator and figure that out as well. There we go. Okay. So that's kind of what we'll do. We'll show you that process too. And again, remember, failing to reject the null does not mean the null hypothesis is true. So if we take a look at this, we look at these counts here, using table C, again, we can see our degrees of freedom here would be 5. We're looking for that value that we have. And again, using our technology, we use that chi-squared go-second vars, and then you'll see this chi-squared CDF put lower, which of course is our chi-squared value, and then the upper 10,000 degrees of freedom, of course, is 1 less than our counts here. And so we actually get a 0.0132. All right. So we'll work on carrying out the test next time. We'll put a stop there. We have some nice exercises there on page 774. I would imagine we want to do those, and then we'll be ready to move on. Until next time, I'm Mr. Boone.